Today we're talking about rate of reaction or rate of chemical reaction and also chemical equilibrium. If we're able to cover the two of them today, fine. If not, next time we continue with chemical equilibrium, but they go together. Now, rate of reaction in short form, remember that as we do, we solve questions. I will not be able to talk too much. We solve some examples from the past questions and how it goes. Now, rate of reaction simply means, in a layman's understanding, it defines how far or how long it will take, are you listening? How far or how long it will take reactants, the moles of reactants, to be converted to products, or how long it will take for moles of products to be taken back to the what? Reactant side. So the rate at which a reaction, chemical reaction occurs, is what we call what? Rate of chemical reaction. So which means some of them can be so slow, while some can be so what? So fast, depending on how the nature of the reactant taking place. Now we define that rate of reaction is equal to number of moles of what? Number of moles of reactant, okay, over what? Time taken, which means it tells us how far, I told you before now, how far it will take for reactants to be completely converted to what? To products. That's what's called rate of a chemical reaction. Now, what we're talking about here mainly now is we'll go and discuss the factors which will make the reaction to be fast or to be what? To be slow. So we talk about factors affecting chemical reaction. Number one is what? Nature of reactants. Nature of what? Reactants. Now, some reactants, when they are in solid form, they don't tend to react fast. Okay? If you use, let me say, crystals or maybe zinc chloride in crystals, and also zinc chloride in completely solid form, the solid one will be so slow to react. It will react anyway, but it will not be as fast as when it is in when it is what? Granulated, like powder form. So that is the nature of reactants. Again, gaseous molecules tend to react what? Faster than liquid what? Molecules. So the nature means at which stage are the reactants? Are they gaseous? Are they solids? Hope you are listening. So are they gaseous? Are they solids, or are they in liquid what? States? So the ones in liquid, in gaseous states, react what? Fastest. But the ones in solids are so slow. That is the rate and the nature of reactants. We talk about what? Catalysts. These are the factors affecting chemical reaction. We talk about catalysts. Catalyst is defined as what? What is catalyst? A substance that can increase, sometimes decrease the rate of chemical reaction to speed it up. But at the end, it's not used up at the end of the reaction. So you can get it back as you put it. What do they do? They only come to make it go faster, but it doesn't take part actually in the reaction. They only help to speed it up or to slow it down. That's what we call it what? Inhibitor. Those ones that tend to slow it down is called what? Inhibitor. But those ones that tend to accelerate it is called what? Accelerator. Okay? So there are two types of catalysts. Then the one that we also call positive catalysts are those ones that increase the rate of the reaction, the speed at which it occurs. Some reactions doesn't occur naturally unless you add what? A catalyst to it. So these are what we call what it does. And every reaction has its own catalyst, because catalysts are specific in their what? Actions. So not everything you do, you put catalyst there, or anyone there. So you have many catalysts, usually manganese and iron oxides. They are used as catalysts depending on the reaction. Another one, we'll talk about another one. Other factor is what? Affect chemical reaction. Anyone you know? Now, sunlight. Now, here is not every reaction anyway. Like, if you want to react methane with HCl, okay, this reaction cannot occur at ordinary temperature unless in the presence of what? Sunlight. Where you can have methane from HCl, you have what? CH2, maybe Cl, and that one again until you get to what? Tetrachloride. And that one is also photosynthesis. These are the reactions that require what? Catalyst to take place. Welcome, sir. So, why is your friend? I can ask him of him. Why is he? So these are the factors that affect chemical reactions. Then another one is what? Surface area. Surface what? Area. What does it mean? Surface area simply means almost the same thing with nature. But some increase in surface area generally increases what? The rate of chemical reaction. Surface area simply means how tiny the substance, the reacting particles are. Okay? For example, you want to react a lump of copper chloride or dissolve it in water. It will be so slow, but when they are grounded, it will be so what? Fast. So the more you ground particles, the more you increase what? The surface what? Area. So normally you know that if you want to add your Maggi in your pot of soup, they use their hand to pieces it. Am I right? Why are you doing that? So as it can dissolve very, very fast, so as to increase the chemical reaction. So these are the factors that can affect chemical reactions. Now, we'll talk about now, there are so many types of reactions. Before I go into other reactions, let me talk about what we call activation energy. Now, there are theories that we are going to talk about which explains how reaction occurs. Okay? We call collision what? Theory. One of them is called collision theory. What is collision? Normally in life, when two things are coming opposite, they do what? They collide, hit themselves. That's collision. Now, coming here now, every particle that's reacting, all the reactants you are seeing here, when you say A plus B, to give us C plus what? D, for example, this could be a metal, an element, or a compound, whatever it is. They contain what? Molecules. If you remember your gas theory, the gas molecules move what? Randomly in straight what? Lines. And as they move, they do collide with themselves and also with the walls of the what? Container. So the same thing comes here now. This is a reacting particle which contains what? Molecules. The molecules are always moving. As they move, what they do? They collide. Now, if the collision between the two molecules is sufficient enough to produce a product, it will give you what? A product. But if it's not, it will collide, but there will be no products, no reaction. So we have those ones that cannot produce. In fact, we have what we call effective collision and ineffective what? Collision. Effective means that the colliding particles of the reactant are enough to overcome the what? Activation energy. Now, I will draw a diagram for you before we go into questions. Now, look at this simple diagram like this. Okay, I'm drawing what is called exothermic. We have endothermic reaction and we have a exothermic reaction. The diagram here represents exothermic reaction. This is A plus B representing the reactants. We have C plus D for the what? Product. Then we have now from the reactant side now, from here to this side is called activation energy, which we use this EA to represent. Okay? This is the energy that these colliding particles must overcome before we can have effective collision. Now, we call here what? Activated complex. Okay? Then other ones also exist. From here now you have what's called change in what? Enthalpy, which is the total internal energy of the system, which we shall go into as we go on. Now, if this collision, if this A and B collide to give you C and D, it means that the energy A and B possess is enough to overcome the what? The energy barrier here called what do you call it? Activation energy, that's EA. So the energy, the energy this A and B possesses must overcome this energy here. Otherwise, if it's less than this energy, there will be no collision. So sometimes you may have so many reactions taking place, which may not give you what, any product. This is because this EA is more than what? Reacting, the energy of the reacting particles. Understood? So that's what we have here. So we'll now go into, let me explain this diagram very well, then we'll solve some problems. Under here now we have the EA here. I may have a diagram here. Please, we call this energy profile diagram. Energy what? Profile diagram. So which is telling us whether the reaction is exothermic reaction or endothermic reaction. You will know it when the answer you get from this, from minusing from here, the product side, delta H, is heat of products, okay, minus what? Heat of reactant. If the answer gives you negative value, it means it's what? Exothermic. Now, let me give it. I have 0 here. Let me say I have 2 here. I have 4 here. I have 6, and I have 8. So this is the kilojoule. Now you are asked to find the enthalpy change from this reaction. Find the enthalpy change from this reaction diagram. What will you do? I said enthalpy change, which is called the total internal energy of the system. That's number 1. Enthalpy change means what? Total internal energy of the system, delta H, or the heat content of the system. Of the system. Now the formula is given is what? Delta H is equal to what? Heat of the product minus what? Heat of what? Reactant. Now this is the product, the reactant now. The product here, am I right? So here should be 1, am I right? Then, which means 1 minus what? Minus 4. What is the answer? That is 1 minus what? 4 equals minus what? 3 kilowatt joule. Now, the answer is in negative form, which means this is what? Exothermic reaction. Even without even solving it, if the product is formed below the reactant, it's also known as what? Exothermic reaction. Even by seeing the diagram, you know. You may also be asked to find the energy of activation, this EA here, from the diagram here. How will you get it? This EA. So you find the number 2, the activation energy. Okay? How do you do it? Look at the diagram again now. The same thing here. What do you have here from here? From here, look at from here to here. Okay? You trace it to this point. You assume this is 8 now. Am I right? Yes, then this is also the product. If look at this diagram, this is my dotted line. From this complex side to where? Reactant side. Not the product, please. Not the product. So which is what now? 8 minus what? Minus 4. Which is what? 4 kilojoule. Not watts. What is in power? Is power. So that is the brief summary of the heat of reaction. Then we're going to solve some problem. The same problem I have here is what you have here. I'm going to give you now. Sorry, it's what you have here too. So we So you have 2, you have 4, you have 6, and you have 8. Now, what does letter X, this X, represent? What does letter X represent?
Activation complex.
Okay, what does letter Y represent? You see Y here? Okay, enthalpy. What is the value of Y? Is it 1? Is it 1?
Yes.
What should be? This is 2, this is 4. Look at this diagram here.
Yes.
Okay?
4 minus.
So here should be what? 4. 3 should be here now.
Yes.
Not 2 now, but 1. So 3 minus what? Minus 4. Product minus what? Reactant. Minus 1. What is the value of the complex here? Activated complex. What is the value? What is the value there? Is it 4? I did not say EA. Activated complex is 8. Okay? Then what about the EA? 4. 8 minus what? Minus 4. Okay? Now, sometimes you may have, I say one of the factors affecting the factors here is what? Catalyst. Now, you may have in this diagram catalyzed reaction. Now, a catalyst normally does, what it does is to decrease what? Is to decrease what? The activation energy. Catalyst only tries to decrease the pathway through which the reaction travels. Bring it down. I mean, from here now, add another one there. From the same point here, have another one like this. Okay? This is the catalyzed what? Part. Okay? I say catalysts only help to speed up the chemical reaction by lowering the activation energy. Okay? So the reaction here is faster than, instead of traveling all the way from here to here, just found a shortcut and give you the answer. So that's what you have there. Now, let me also talk about some. I told you about endo and exo. Now, before I go to another one, let's talk about endodynamic reaction. A reaction that, hold on please, that gives out heat to the surrounding is called what? Exothermic what? Reaction. The vessels become so hot because the heat is being released. And I told you that, how do we know again in diagram? The enthalpy change is always negative. Then for endothermic reaction, it absorbs heat from the what? Surrounding. The enthalpy change is always what? Positive. Now, and the product of this one is formed above the what? Reactant. So you can know it in so many ways. Either you solve it or okay. Now you have like this. This is reactant and this is what? Product. So this is what? Endothermic reaction. How do I know? It's positive. And the product is also formed above what? Now, how do we get the enthalpy change now? Which of the areas is for enthalpy? Enthalpy change in heat content. Is it from here now?
Yes.
Like, you say yes? From here? Or where? Or like this down? Remember, it goes from the reactant to the what? To the product. Here is now the delta what? H. And why is it called delta H? Because it's a change. Something minus something. And the formula remains the same. Heat of what? Products minus heat of a reactant. Give yourself, Mr. Man. Heat of what? P minus heat of a reactant. That's what you have then. Now we are turning into a laughing jackass. So that is majorly about. Now I want to ask us, what are the collision theories? Collision theory. You can say it for me. One. No, number one. Okay. A chemical reaction can only occur, okay, if the reactant possesses enough energy that will overcome the what? Activation energy of the reaction species. Okay? I say that these are the reactants now. It must have enough energy that will overcome the what? This energy. This is energy barrier that must be either it is here or that it is here. I must overcome. So if the energy barrier is more than the reacting energy of the reacting particles, there will be no chemical reaction. It will lead to what? Ineffective what? Collision. But if the collision is the energy is more or equal to the energy of this species, there will be what? A collision. That's the major theory. The other ones are also supporting the same thing. Okay? So now there are three forms. I talk about enthalpy change. Enthalpy change is what? Is the total internal energy of what? Of a system. And we use H to represent it. Then change in H is what? Delta what? H. Then there are other energy particles that are possessed by reactive species. We have the free energy and we have the what? The entropy. Okay? We have the free energy and we have the what? The entropy. Then all of them sum together give you what? The total, that is called total internal energy. And the two of them are, now entropy simply means what? The degree of randomness of a system. That's entropy, the degree of randomness of a system. How random or how quiet? A very quiet substance has a very low entropy. But the more crowded, the more it moves, the more what? Entropy it has. Like for example, an ice block has a very low entropy. Boiling water has a very high entropy. We use what? S to stand for what? Entropy. Now, if I use delta here, delta stands for change. The real symbol here is what? H, please. I'm not talking about delta now, means there's a change, something minus something. Then what is the entropy again? S. But if I use delta S, it stands for what? Change in what? Entropy. Okay? Now, in entropy, because if we talk about entropy, we talk about what? Temperature change as well. Now I say that if you have an ice block, very cool ice block, very, very cold, a low temperature now, it's very low or even almost zero entropy is there. But when you begin to heat it, why are you heating? When you're heating, you're doing what? You're increasing the what? Temperature. Okay? So whenever you add it here, I'll put it sign for what? Temperature in Kelvin, not in degrees. If you are solving it, you must convert to what? Kelvin. Plus what? Change in free energy. Change in what? Now, the G stands for free energy. Normally, you call it Gibbs free energy. So also have what we call standard free energy. Now, if you add the other together, now from here now, if you have this delta H, which is the total internal energy, which means added together, from here you can bring out the other one, am I right? You can find T delta S now. From this equation, you can bring out this formula. You have that T delta S, give us what? Delta. Remember that I want to assume that here is remaining. Hold on. Here is staying here now. You bring out this one. Okay? So, delta H minus what? Minus delta G. Okay? Now, if you have to find only the entropy, change in entropy, what do you do? Change in entropy now, which means delta S is equal to what? Delta H minus delta G. Exactly. Over what? Over T. So that's the formula. Now you can also find out, bring out here too as well to solve it. So with formula, you can actually find entropy, enthalpy, and Gibbs what? Free energy. This formula connects the three of them. That's why it's called total, very important. Some call it the heat content of the system, some call it the total internal energy, some call it enthalpy. Anyone that you like use is also correct. Now, let's also go to chemical equilibrium. Okay? Now, chemical equilibrium, because they are together, these are all reactions. In chemical equilibrium, we talk about reactions that can go either forward or what? In fact, there are always two ways. Forward and what? Backward. That is simple we used to know. Now, in definition, chemical equilibrium is a state of a system in which there is what? A reversible change in the system with what? Respect to time. In science, time, is of essence. Okay, which means if it takes 1 second for the reactant to give you what? The product. It's assumed that it will take the same 1 second for this product to decompose to give you the what? The reactant. You must have 2 arrows here, which represent what? Reversible reaction. So whenever you see this arrow in any reaction, it means it's what? Reversible. You can go it that way. If you do the A and B finishes reaction to give you C and D, and it is done in a closed system, to have a perfect equilibrium, it must be done in what? In a closed system, where nothing goes out, nothing does what? Comes in. Okay, in this case now, as soon as the A and B finish reaction, the C and D begin to do what? Decompose. And if it takes, like I told you, if you have R1, which the rate, remember that rate is equal to what? Volume over what? Over time. Okay? The amount, volume now, the quantity of the reactant over time taken. Okay? Now, if it takes 1 second for this A and B to completely react, to give you C and D, it's assumed to take the same what? 1 second, we use R2, rate 2 for this C and D to give you what? Back A and what? And B. And factors also, the same thing we have here now, also affect what? Chemical equilibrium. The same thing we have here, but there are small differences. Now, I will pick some of them. One is what? Temperature. If we must talk about temperature, you must consider whether the reaction is what? Endodynamic or exodynamic. There must be a sign before they can be asked about temperature effects. Now, if I say that H2 plus S give us H2S. Now, if I argue that delta H is equal to what? Negative. Which means that it is what? Exodynamic reaction. Now, what will be the effect of increased temperature on this reaction? And how do we know it? You look at the sign here, number 1. Without this sign, you'll not be able to know. Unless it's a normal reaction that occurs every day in life, like burning of substances. It's always what? Exodynamic. You don't need to measure it. But in this case now, you have to have this sign to know whether it is endo or exo. Now, it is exodynamic reaction now. How do we know that if you add more heat to the system, which means if you increase the what? Temperature, will it affect forward reaction, forward or backward reaction? In this system, we have what we call forward reaction and backward what? Reaction. Or right and what? And left. Okay? Now, increase in temperature now will favor which side? Is it the right or the left? The left. Why do you say the left?
Because it's already in.
Yes, it is left correctly because the right, this sign is for the what? For the right hand side, not for both. Which shows that here is already hot. Because it's already hot, if you add more heat to it, it will shift the excess heat to the what? To the left to balance the equation. That's what the man whose name is what? Le Chatelier. Principle states that if an external constraint, an external factor or factors such as change in temperature, pressure, and what? Concentration is imposed on a system in equilibrium, the equilibrium will do what? Will shift so as to cancel the effect of the constraint or factor added to it. When something is in equilibrium, it means it does not need disturbance. It's okay, it's quiet, it's resting. If you do anything there, that is bound to what? Change. Now, this reaction is assumed to be in equilibrium. It's okay like that. Adding any other thing there will do what? So this will have to shift so as to cancel this effect. That's why you have to shift this heat to the left to cancel this effect here. Because here is already hot. It's boiling with it's very hot, and you're adding more heat to it. So to balance the equation, you say, please give to my what? To my left, because here I'm already okay. I'm hot. Now we'll talk about the effect of what? Pressure. Pressure will only affect the equilibrium system if they are all in gaseous state. That's the thing about the pressure here. Even here, you have us here. but they must be what? All gaseous. Now, if one of them is solid or one is liquid, it cannot, answer will be what? There will be no effect of what? Pressure. Now, I dissolve this. I have NaCl aqueous, or let me say solid here, to NaCl aqueous. Here is a solid form, here is a what? Liquid form. What will be the effect of pressure on this system? Any effect here? Why? Because they are not what? In fact, no one is being asked here. Now, please, I say number one, if you must have pressure effect, number one, they must all be what? Gaseous. That's number one factor you must consider. If any of them, one is solid, one is a gas, one is a liquid, the answer is what? Pressure will have no effect. Number two is that there must be difference in volumes on both sides. There must be what? Difference in volume on both sides. If they have the same volume on both sides, there will be no effect of what? Pressure. For example, I have this something like that. I have nitrogen, let's form ammonia, nitrogen gas, plus hydrogen gas, then giving us ammonia, or in ammonia gas now. Now, you are asked to, what is the effect of pressure on this reaction? Now, number one, I say there must be what? All gaseous. Number two, there are all gases here, am I right? Number two, there must be what? Difference in what? Volume. And when there's difference in volume, then increase in pressure favors the side with what? Less volume or moles. You got the point? Increase in pressure favors the side with less volume or what? Moles. That's number one you must know. And vice versa, which means decrease in pressure favors the side with what? More moles. Watch out now. How many moles are here or volumes? Anyone you like is okay. Either mole or volume you choose to use. Now it's balanced 2 and 2 for nitrogen, am I right? 2 times 3, 3 times what? 2. Then what is the effect of pressure on this system? It will favor, use the word favor which side? Remember I said, I'm open. I say, what is the effect of pressure? I did not say increase or decrease. So you should answer it in two ways. I don't say effect of increasing or decreasing pressure. I say, what is the effect of pressure on this system? Increase in pressure. Okay, follow my own word. Increase in pressure favors which side? Forward reaction, right? Why do you say that? Because how many moles are here? 4 moles, correct. And here is how many moles? 2 moles. So increase in pressure favors the side with less number of moles, which is this side now, less number. And another way around, decrease in pressure favors the backward, yes, the backward what? Reaction, because it has more moles. Understand? Now, another one is, please, I've spoken about temperature and pressure. Another one is a change in concentration. I want to use same English, same example here. Change in concentration. Now, what will be the effect of, that's number 3 factor now. Okay. What will be the effect of removing the ammonia from this reaction? The amount of ammonia produced here, as produced, as mean it is done in an open system. You know, I say you can never achieve equilibrium in an open system. It must be in what? A closed system. So now, but assuming it's open now, that as ammonia is formed, it's being removed. What will be the effect on the system? Which side will it favor? The left, am I right? Now, if ammonia is removed, it means that more reactant will do what? Will collide to replace the what? The product. So removing this ammonia favors which side? I want to hear that out. Is it left or is it right? See my right, see my left. What are you saying? See right now, see left. You're saying left now, you're saying right. No, use here as right. Let me help you. Use here as right. Okay, this is always right, please. This is always left. Then, removing ammonia favors which side? The right one. No more left again. You're saying left one. Now, it will favor the what? The right hand side. You know, this thing is already in equilibrium now. It's balanced. That's equilibrium now. That's normal language. It's balanced in a balanced system. So if you now remove this one, it means that this thing will now bend down. But you're still on a bench. One on this side, one on the other side. Davina is fat. She sits on this side. You know you're not fat as Davina. You stay here. Thank God that the bench is balanced, okay? Suddenly Davina start telling you. What will you do? The bench will do what? So this is now. So this is like being in a balanced what position now, but you have removed this side now. So this thing will have to do what? More of these will combine to replace. They want to pay back. Now what man is saying here that if an external factor is imposed, any factor, whether temperature, pressure, or what, concentration is imposed, added to what? To what? The equilibrium system now. The system naturally on its own will try to do what? Adjust. So as to what? Cancel the effects. So you have removed this one now, so you know balance. More of this will do what? Collide or react to produce what? So it will favor the more you remove ammonia, the more is being produced. But the other way around, if I remove any of this reactant, if I remove any of the reactants, assuming N2 will be removed, what happens? Who will eat that eat now? What is in your eat? The ammonia will decompose to pay back the what? The nitrogen. So therefore, removing any of the reactants favors the what? Backwards reaction. Removing the products favors the what? Forward what? Reaction. So these are the major factors, 3 factors. You must know how to identify them in the equation. That's the major thing here. How to answer problems there. Sometimes you may have something like this that doesn't make sense, and you ask you what are the effects. Now N2 plus O2 give us, look at this equation. Now you have this also in the system. Now tell me the effect of increased pressure on this reaction. Sorry, what is the effect of pressure here? Look at it very, very well. What is the effect of pressure on this system? You see what I was telling you? Pressure have no effect here. Why? Because they have the same number of what? Moles. You must not forget the factors. It's not about knowing how they affect. You must know the factors that are, for this pressure only, you must know the factors that are responsible for the change. If they have the same moles on both sides, mole means volume, in this case now, pressure will not have any effect. There must be a difference in what? Moles or volume. 1 plus 1 is 2. Also what? 2. So, no, and though they are all gases anyway, I agree. But they have the same moles. So answer will be what? No effect of what? Pressure. So I told that for temperature now, they must give you what? A sign. I may have delta H here is what? Minus 25. Not for example anyway. Or just negative. It shows that this is what? An exothermic what? Reaction. Which means that increasing the what here? Temperature favors the backward what? Reaction. But what if here it becomes positive? It favors what? Forward reaction. Because it means here is cold. Endothermic reaction now. So if you add more heat, you'll be happy. Please add more. I'm feeling cold. It will like it. And vice versa. So you must be able to identify those products, those things. Now we'll talk about I'm trying to talk about equilibrium constants. Now, all in Jamb, we will not be asked to prove anything there. Unlike WAEC, this is exam class. So they will give you equation. You are to identify the constant. For example, I have N2 gas plus O2 gas give us 2NO gas, and we'll be asked to write the what? Equilibrium constant of this reaction. That's KEG. Now, what we have there is that always balance, yes. Now, equilibrium constant simply means what? Moles of the product over moles of the what? Reactant. Okay, in multiplicative form. So now you're going to have it as constant C is equal to 2NO over what? Over what? N2. Now you have it like this. Now, how many moles are here? 1 mole. So look at 1 here. Is that any important? No, 1 is 1. Then, and what again? O2. What is here? Now, for this 2NO now, do you see it? Now, the product raised to the power of each mole of their moles, if there are 2 anyway. Okay? The product raised to the power of their moles, or of each moles, over the reactant to the power of their what? Moles. You know what I'm saying now? Now, let me give you an example. You have this now again. Gaseous give me 2NH3. Now, write the constant here, the constant of this reaction. Deduce the equilibrium constant of the reaction above. Give me the answer first. Hope you are doing it. Let's go into free fast. Let's go into past questions. What is the answer then? N as KEG is equal to what? NH3. Raised to in bracket, please. You change this plus to what? To times. We use dots. Power 3. Is this 3 or 2? Power 2 now. All over what? H2. Is this a mole? A mole? What is it called? No. If I have atoms, the number of atoms it has now. Moles are written behind, okay? So I say to the power of their moles, not atoms. Understood? Then you have H2, then how many moles are there? 1, 2, nothing like that. Dot, if you want. What again is there? N2, am I right? Yes. Power what? You understand? That's KEG. So you can use the right other ones as long as you want. Now, please, I want to get some questions to answer it for me. Now, look at this question. Are you listening? Which of these equilibria, are you listening? Which of these equilibria is unaffected by a pressure change? Which of these equilibria is unaffected by a pressure change? Can I write it down, please? Which of these equilibria is unaffected by what? Pressure change. A, 2NaCl solid. 2NaCl solid plus 2Na. 2Na solid, then arrow. 2Na plus Cl2. Cl2 is gas. Na is solid. Number 2, H2 plus I2 hydrogen plus iodine give us what? Hi. 2Hi. Number C, or option C, O2 as 2O2, 2O like oxygen. Then 2 arrows, 3O2. That one is 2O3. Make it 2O3, please. 2O3. Then 3O2. It's also a gas. Then finally, you have another one that says 2NO2 gas, double arrow, N2O4. Which of them will not be affected by pressure change? Yes. What did A say? That one is out of point, okay? Because it's a solid and what? Is not any gas there, Steph?
Yes.
But it's a solid. So far there is one solid there, that one is what? Out of it. You eliminate. Number 2, it's correct now. Then what is this? It says A and C. What is this? C say? C is what? A and B.
Yes.
What did B say?
Gas.
Here? No, it's a gas.
Yes.
The all gases, yes. In this case now, it's gaseous form. You know, iodine can do what? Sublime. You know iodine now, it can be in any form. It undergoes what? Sublimation. Only one thing now. So, is it wrong, actually?
No.
So, answer is only what now? Answer is only A. Okay, on both sides, one? Okay, 1 plus 1 is 2, am I right?
No, A doesn't have the same number.
No, what now? 1 is here.
A.
Plus. No, A is correct now. It's out of it. I agree. But here is also what? 1 plus 1 is not 2. And 2 here. So it's also correct. A and C. Okay? A and B. That's one. Then another one. Please help me write this one down. ME. Okay. We'll try to meet up with time. ME, I write it down. ME, small m and capital A. Like this. That M stands for what? Number of moles of E is the reacting species. Plus NF. Then that other is PG plus QH. P small. PG plus Q what? H. You are asked here to write the equilibrium constant. In above reaction, the constant of the reaction above is given by dash. Then you can write it now. There are options there, but you can do it by yourself, am I right? How do you do this? Products to the power of is what? Mole times is here now. So we just write G is the species in bracket what? P dot. What are you going to have there? H power what? Q all over what? Reactant, which is what? E raised to power what? M dot F to power N. Just always know that it's always the product first on top to the power of their moles. If there are two as I have it here, change this to what? Multiplication sign. You can just use dot or nothing may be here. Doesn't matter. A number of that sign is what? Multiplication. So that is how, please, I would like to call it a day because for today, I know. When someone appreciates. So